All right, guys, so in the last video, we went over valence electrons and how they help with bonding. In this video, we're going to talk more about that losing and gaining electrons and what effect that has on the overall charge of each atom. And that's, what that term is to describe that. So watch that one first because I'm just piggybacking off of that. And we know that the valence electrons can be lost or gained. That helps us, make new compounds, things like that. So here we have beryllium, sulfur. They're a match made in heaven. They found each other. One of them needed to lose electrons. One of them needed to gain. So beryllium was like, hey, sulfur, I'm going to give you my electrons and we are going to be bonded and we are going to be happy forever. So let's think about this. If beryllium, where's my drawing tool? Okay, so if beryllium lost 2 electrons, remember originally he had 4. So he had 1, 2, 3, 4 negatives, and of course he had 4 positives because he was neutral because 4 is his atomic number. He needs to lose 2 to be happy. So if he loses 2 of these electrons, what is his overall charge? Pause the video, ask yourself, replay it when you have an answer. Hopefully you realize that -2 plus +4, his overall charge is going to be +2. We call this number here, its charge, the oxidation number. The oxidation number. And this charge is really important because that helps us determine, who he's going to bond with. Not only that, but what the ratio of each atom is going to be. Now, sulfur, like I said, they're a match made in heaven, and we're going to find out why. So sulfur had how many? 16 total electrons. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Woo! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. 16 positives, 16 negatives. He gained 2 electrons, right? He gained 2 electrons. So if he gained, pardon that. If he gained 2 electrons, well, now he's going to have more electrons, more negatives than he does positives. So more negatives means he's going to have an overall negative charge. His oxidation number is going to be -2. That's his charge. And if we put a +2 and a -2 together, well, that magic equals what? What's +2 plus -2? It equals 0. That means it's neutral. Its charge is 0, and that's what all elements are, before they undergo this oxidation change. That's what all compounds are. They want those charges to cancel out, so it works out quite perfectly. Again, we know that the oxidation number is what it is based on if it loses or gains, based on its valence electrons, based on, this little visual that we drew. But there's an easier way. There's a pattern, again, looking at the periodic table. So we can say that looking at hydrogen, lithium, sodium, these alkali metals, they all have 1 valence electron, right? They're in group 1. And so instead of gaining 7 negatives to be happy, they're just going to lose 1. And if they lose that 1 negative, they're going to become positive. So their oxidation number is +1. Then here we have these alkaline earth metals, ALKALINE, alkaline earth metals, and those guys have 2 valence electrons, which they're going to lose in order to be happy, so they're going to have a +2 charge. Over here, the pattern continues. These guys don't have a name. They're boring. Their charge is +3. Their oxidation number is +3. Then we get to carbon. So if we think about our visual over here, if I have carbon, he has 6 electrons, 2 of which are valence, 4 of which are valence. 2, 3, 4. Well, in order to be happy, carbon can gain 4 or he can lose 4. Well, which one's he going to do? I don't know. It depends on who he's bonding with. Is he going to go with someone that needs to get rid of him, or is he going to go with someone that needs to gain him? We don't know. We can't predict. So we just skip this column when it comes to oxidation number. We skip. I'm just going to put a delta. Delta means change, right? Or skip. So I'm going to skip that column. And let's jump over to nitrogen. Nitrogen has 5 valence electrons. He can either lose those 5 or he can gain 3. I would rather gain 3. And if I do, I gain 3 negatives, so I'll have a negative overall charge, specifically -3. Sulfur and oxygen, we already determined that those are a -2 oxidation number. And then finally, -1. We have our noble gases. They don't want to lose. They don't want to gain. They're already happy. Do not mess with them. Their oxidation number is 0, just like every other element on the periodic table until it undergoes that bond, that change. Then that's where those oxidation numbers come in. So I'm just going to give you another visual for beryllium and sulfur. So again, we have beryllium, and he's going to try to, where's beryllium at? He's going to try to lose those 2 valence electrons, and he's going to get that +2 charge. Beryllium, he's going to get that +2 charge. And then we have sulfur, he's going to have that -2 charge. And so if we put a beryllium together with a sulfur, they're going to make that exchange happen, and it's going to become beryllium sulfide. Now, you don't need to worry about this part right now. I'm just talking about the charges and how they cancel out. Being able to visualize those valence electrons is a really great tool to have. And I can do it in my head, but looking at this, you might not know where that came from. So we use something called a Lewis dot structure, which is what we're going to talk about in the next video to help make this relationship and how these go together to make this a little bit more clear. So for now, what you need to take from these first 2 videos is valence electrons are on the outermost shell responsible for bonding. It's all about losing or gaining electrons. Once they do that lose or gain, they have to have someone to give or, get to, and we're going to get that oxidation number. Everything on the periodic table is neutral until it undergoes that change, at which point that's where these charges come in. Any charged particle is called an ion, and so these are responsible for ionic compounds, which is what we see here. Again, we're not quite there yet, but that's kind of our end goal. That's what we're working towards.